Hello everyone. So we already have discussed different considerations related to device analysis so far. There are many other discussions still left as far as the devices are concerned. And before we started device analysis, we discussed carrier concentration, access carrier concentration, transport equation, continuity equation, and then we slowly entered into the device part. We already have started PN junction, and we discussed what is the structure of PN junction, how a PN junction physically looks like in a schematic diagram, and we discussed the width of different layers in that PN junction device. We also have discussed different other considerations inside an PN junction. For example, in the last lecture we have discussed started built-in potential, built-in electric field and associated discussion. And before that, we also have considered different assumptions that usually we take when it comes to device analysis. As far as the device analysis is concerned, I already have said before that we don't consider the entire device as a whole. We only consider a portion of it, a part of it. We already have discussed this. And there is a reason behind that, because if the major phenomena is happening in a particular portion of the device, there is no point in bringing in other associated things into the discussion, because that will unnecessarily complicate the entire discussion. So in this regard, we also have discussed different assumptions. What are the different approximations. We also have considered the geometry of the device, and how this geometry has been reduced to one block-like structure, because as I've said, the entire device is far more complicated than the box that we usually see in the books. So in today's discussion, we will again discuss little more about built-in electric field and built-in potential. What are those and why they are important? We will then go to the equilibrium analysis in PN junction. So as I have said, equilibrium is a very important concept. When we were discussing the equilibrium steady state, we already have mentioned that why equilibrium is important, why people start discussion on equilibrium. Today's lecture will cover the built-in electric field and built-in potential, and at the same time we will start the equilibrium analysis of PN junction. Let us start the lecture and understand these concepts, and then we will again discuss about the summary of that particular lecture. We already have discussed few details about PN junction. In the last lecture, we've seen the details regarding the built-in potential, and we also have derived the equation for the built-in potential. Here is a step-by-step explanation of the same, although I have discussed it in the previous lecture. I also have discussed the built-in electric field and the expression for maximum built-in electric field. So here again is a kind of detailed analysis of the same. And thereafter, I also have discussed the depletion width and the physics associated with the depletion width. So today we will start with band diagram in PN junction under equilibrium. So as we have said previously, that the approach towards device analysis is first you divide the entire device into two different regions. For example, in this case, the device is divided into neutral region, and then you have space charge region, and here again you have a neutral region. So there are two regions, one is neutral, another one is space charge region. And I already have explained why we consider only the P plus and N part in the device. So the device that is under consideration is kind of a box with a P plus and N region. That I have already discussed in previous lectures. Now, to begin with the band diagram, we would first see where the Fermi level lies. So, in case of equilibrium condition, we know that the change in the Fermi level with respect to x is 0. That is, the gradient of the Fermi level with respect to x is 0 under equilibrium. Then you have a constant Fermi level throughout the device. And we also know under equilibrium, the quasi-Fermi level for both electrons and holes are same. So, both the Fermi levels are actually EF. They are not kind of different in case of equilibrium condition. So, you can draw the conduction band in the neutral region as a straight line parallel to the EF, that is Fermi level. Throughout the neutral region, the conduction band will not vary. So it will be parallel to EF, a straight line parallel to EF. And the valence band in the N side neutral region. So we are considering first the neutral region in the N side. So the EC is constant, as we have discussed. Then you can very easily find the EV, which is EG away from the conduction band. EG is the band gap. So you can just calculate the difference and you can draw the EV. So EV also will be a kind of straight line parallel to EC and EF both. So in the neutral region, you know now EC and EV in the N side. Now let us see what will be the case in case of P side neutral region. So in the P side also, you will find your EV is constant, but the difference between EF and EV will be smaller than EC and EF because the doping level in P side is higher. We consider P plus, that is the doping level in the P side is higher than that of N side, and that explains why your EV should be closer to EF compared to your EC-EF difference. So you can draw the EV closer to EF, and then your EC in the P side will be again EG away from EV. That is also a straight line parallel to EF and EV. And if you want to quantify the gap between EC and EF, it is nothing but Q VT ln NC by ND, right? And the same thing in the valence, the same thing in the P side will be this Q VT ln NV by ND. So this is the difference between ECF and EVEF. And the band diagram in the depletion region or space charge region will be a straight line connecting these 2 points, right? And that will be a continuous line. Why? Because the gradient of the EC determines the electric field. Now, if there is a discontinuity anywhere in the depletion region, that will indicate an infinite electric field, which is not a practical case. So, definitely the band in the depletion region will be continuous. So, you can directly connect EC and EC in the P side with the EC in the N side. And then similar to the EC, you can also draw the EV for the depletion region. We already know the bands in the neutral region. For depletion region, just connect it with a continuous line. Now, similarly, you can also draw the E0, that is vacuum level. The vacuum level will be QXN away from the EC. This is not XN, this is basically a kappa. which is nothing but the electron affinity. We already have discussed these things previously. So again, you will have an E0 which is following EC because the difference between E0 and EC is constant throughout. So you have E0 also drawn in here. And your intrinsic level, that is EI, will be in the middle of EC and EBI. I have shown it using a dotted line. Okay. So this is more or less the band diagram in PN junction under equilibrium. So this band diagram is drawn considering two principles. The first principle is EF is constant with respect to X. And we already have said why it is constant. Because under equilibrium, from the transport equation only, you know, Jn is equal to 0, Jp is equal to 0. Now, if you consider this transport equation in terms of the quasi-Fermi level that we already have done previously, then you will find that the gradient with respect to X for the quasi-Fermi level is 0. That means it is not changing with respect to X. And the quasi-Fermi level for electrons and holes is same in case of equilibrium condition. So ultimately your EF is constant with respect to X. This is principle number 1. And the second principle that we considered is continuity of the band. So each of these band will be continuous. So if you say the continuity of band E0, that itself will ensure that EC and EB is continuous, because the difference between E0 and EC is constant, which is Q kappa n. This Q kappa n is showing the energy, okay? That's why this charge term is here. So please don't confuse it, why Q is here. So it's just converting it to a energy. This particular y-axis is nothing but electronic energy, right? So E0 minus EC is always constant, and similarly EC minus EB is also constant. That is the band gap. EC minus EB is nothing but the band gap. So you will find if E0 is continuous, EC and EB also will be continuous. So that second principle that we considered is continuity of the band. Now one thing that you also should remember here is it's an homojunction. Homojunction means both the P and N regions are on the same material, both are silicon. So there is a case for heterojunction also, but let us not complicate the entire situation. So the heterojunction is beyond the scope of this particular analysis. So here this is a homojunction. Both the P and N type doping is on silicon only, or on a same semiconductor material. Now, apart from equilibrium, even if you consider quasi-equilibrium, that is Jn and Jp is not exactly equal to 0, but they are approximately equal to 0. There must be some difference in quasi-equilibrium. There exists some difference in quasi-equilibrium, but you can approximately take Jn and Jp both equal to 0, approximately equal to 0. In that case also, you will find that your quasi-Fermi level, the gradient of quasi-Fermi level, that is dfn by dx or del fn by del x, is approximately equal to 0. Okay. So at quasi-Fermi level also you can consider these two principles. Okay. Now we know that the device analysis is nothing but solving the 5 basic equations. So here I am showing you, even in the band diagram, we considered those 5 basic equations. So one of the first equation is the transport equation. And once you solve the transport equation under equilibrium, that is Jn equal to 0, Jp equal to 0, then only you will get to know that EF is constant with respect to X. We already have seen that. So the transport equation gives us the information that EF is constant with respect to X. So that is what our starting point was. Then from the continuity equation, you will find that delta N and delta P is equal to 0. That means excess carriers, the concentration of excess carriers is equal to 0. That will give you the information that EFN is equal to EFP is equal to EF. That means the quasi-Fermi levels are same for both electrons and holes. So from that equation, the continuity equation, solution of the continuity equation gives you the information that the EFN is equal to EFP is equal to EF. And from Gauss law, we will be able to calculate the shape of the band, especially in the space charge region or depletion region. The shape of the band is, in this case, parabolic. We already have seen the similar information while discussing the built-in potential and etc. So this shape of EC, EB, ED and EA is nothing but the doping levels, doping energy levels. So all this information you will get from Gauss law. So this 5 basic equation gives you all the information required for the band diagram. So it's not like that two things are completely separate. They are actually related to each other. And XD is your depletion width. Okay. Now, let us move forward and see what is the IV characteristics of a PN junction. And to begin with, let us first take the example of forward bias. Forward bias means the diode or PN junction is connected in this fashion. That is, the positive terminal of power source is connected to P side, negative terminal of the power source is connected to N side. The forward bias characteristics is something like this. So initially it's very low current and then it will start increasing exponentially as shown in this plot. So let us first analyze the forward bias case. So here the circuit is shown with respect to the device. Your positive terminal is connected to the P side and your negative terminal is connected to the N side. So essentially this part is positive and this part is negative. And in this case also we take approximation. So the first approximation is the width of P and N region should be much higher than the diffusion length. This approximation we already have discussed in our previous studies. So this is the first approximation, that XP and XN, that is the width of P and N region, should be much higher than the diffusion length. And the second approximation that we take is the applied voltage V is very small. And this ensures that the device is in quasi-equilibrium state. Quasi-equilibrium means a small disturbance from equilibrium. So this is only possible if the applied voltage is very small. So in this case, we take this approximation that V is small enough to ensure quasi-equilibrium in the device. And hence, in such a situation, you can consider the neutral region as quasi-neutral region in both the cases. So these are quasi-neutral region. And then you have the space charge region in the middle. Another approximation that we take is there is no voltage drop in the quasi-neutral region. So whatever you apply, this voltage will appear across the space charge region. So if you analyze it, you will find that the V is distributed in the neutral region in the N side, which is given as Vn, neutral region in the P side, which is Vp, and the across the space charge region, which is Vd, space charge or depletion region. So we call it as Vd, right? So the total voltage V is actually equal to Vn plus Vd plus Vp, right? And we consider Vn and Vp both is very small compared to Vd. So you can neglect these two. These two you can consider as 0. So your V is approximately equal to Vd. That is one more approximation or assumption that we take. So whatever you are applying as an external voltage will appear across the space charge region. So your Vd is approximately equal to the voltage applied, that is V in this case, right? So let us first study the forward bias condition with respect to the band diagram. So this is the band diagram in forward bias condition. We already said we are considering quasi-equilibrium situation because you are applying a voltage, external voltage. So definitely the device will not be in equilibrium because you have an external stimulus, that is a voltage. But we kept the voltage low so that the device remains in the quasi-equilibrium situation. Okay. So in this quasi-equilibrium, you have three different regions: quasi-neutral in the p side, quasi-neutral in the n side, and then you have space charge region. Now, we already have discussed, once there is a space charge region, there will be a built-in electric field, and the built-in electric field will be from N to P. So there will be a built-in electric field from N to P. And then you have applied a very small voltage V. So you will have an external or electric field due to external voltage, that is shown over here, which is termed as E external. That is the electric field due to external voltage. Now, as you have considered that the external voltage is very small, you also can assume that the external electric field or the field due to external voltage will be smaller than the built-in electric field. So you will have a resultant electric field, which is this one, and this particular electric field is your resultant electric field and can also be termed as electric field in forward bias. So E forward bias. This will be smaller than the built-in potential because there is an electric field in the opposite direction due to external voltage, right? Now, in such a situation, you will find that your depletion width, that is the width of the space charge, will shrink because now you don't have a built-in electric field which is as high as the equilibrium condition. So some portion of your built-in electric field will be nullified by the electric field due to external voltage, that is the E external, and that's why there will be a shrink in the space charge region. So if you draw the electric field, that is the forward bias electric field, you will find that the forward bias electric field will be a bit less than that of the equilibrium condition. So here first I have shown the electric field in equilibrium condition using this dotted line, and then I also have drawn the forward bias electric field with this blue line. Okay, so this particular electric field will be of the similar shape because the phenomena what is happening inside is same. But in this case, you have a electric field in the opposite direction, and that's why the XD in this case, whatever is the XD in this case, say this much, right? This is your XD. So your XD in this case will be less than XD0, that is the depletion width in equilibrium. And the area inside this electric field is denoting the electric potential. Area inside a curve is nothing but the integration of that particular function. So integration of the electric field will give you the potential associated with that, and this particular area or the magnitude or value of this particular area will be psi 0 minus V, where psi 0 is the built-in potential. The built-in potential due to built-in electric field under equilibrium. This psi 0 shows the built-in potential. And now this particular area will be psi 0 minus V. V is the external voltage, right? So the area will be psi 0 minus V. And if you now write the expression for XD, we already have derived it. So the expression for XD, you will find previously it was 2 epsilon psi 0 but now it will be 2 epsilon psi 0 minus V, because that is what your effective potential. So it's 2 epsilon psi 0 minus V by Q into 1 by Na plus 1 by Nd. So this particular term has reduced, so definitely your XD also will reduce. Mathematically also, you will find that your XD is smaller than the XD0. XD0 is nothing but the XD under equilibrium. Okay. Now, let us find out the concentration across the, or concentration throughout the device. Now, if you plot, say, only the whole concentration, we are not going into the electron concentration because both of them will be more or less same. So let us only consider one carrier. That will simplify our discussion. So we are considering only the whole. In that case, in the P side, it's majority carrier concentration. Let us first see what is the equilibrium concentration. So it will be something like this. So in the neutral region, or quasi-neutral region in this case, the concentration PP0 will be constant till it reaches the depletion region. And then similarly, the Pn0 also will be constant in case of equilibrium. So it is shown using this dotted line. And then both of them will be connected with each other like this. That is what we already have discussed previously, that in equilibrium, this is what the concentration is. Right? Now, in this case, you will find due to the external electric field, there will be an excess carrier in the N side. We are only considering the holes, right? So there will be an excess carriers. So you can easily say that in the depletion edge towards N side, that is here, the carrier concentration will be higher than that of the equilibrium. So somewhere here. I repeat, because of the external electric field, there will be a generation of excess carriers, and that's why the concentration of minority carriers will increase. Why only minority carriers concentration will increase? Because we are considering low injection level. So here we are invoking another approximation, that is low injection level. So we already have discussed under low injection level, majority carrier concentration remains constant. Only minority carriers concentration will get affected and they increases. Then they get increased, right? So as we are considering the whole is the minority carrier in the N side. So the new concentration under quasi-equilibrium situation, where you have an external potential or external voltage, you'll find that the concentration is a bit higher. So now in the space charge region, the new concentration graph will be this one, right? And in the neutral region or quasi-neutral region, you apply the diffusion approximation. So diffusion approximation is valid in the neutral region. And the solution of the diffusion continuity equation, if you solve the continuity equation we solved previously and have seen that the nature of the equation is exponential. So in this case, you will find this particular plot is, slowly going down and will meet with the equilibrium situation at a certain distance. So this particular length is, we consider this particular length is sufficiently large. So at some point it will meet the equilibrium condition, but near that depletion region you will find there is a exponential nature. Kindly note this particular y-axis is in the log scale, right? Now this is what the carrier concentration nature will be. Now you can apply the Boltzmann relation, that is psi naught is equal to Vt ln pp0 by Pn0. That is the Boltzmann relation under equilibrium, right? When you consider Jp and Jn is equal to 0, you can apply this particular Boltzmann relation. We already have seen the Boltzmann relation previously. If you don't remember, kindly go to those lectures and just have a look. Now, in this case, why your Jp and Jn is equal to 0? Because your drift is equal to diffusion. But in this case, as you have an external potential, your Jp and Jn will not be exactly equal to 0. Rather, it will be approximately equal to 0. So the same Boltzmann relation will reduce to this one. So in the left side, it will be psi 0 minus V approximately equal to Vt ln pp by Pn. Now pp and Pn are the concentration under quasi-equilibrium. However, pp0, Pn0 is concentration under equilibrium, right? So in this case, your pp will remain same because this is the majority carrier. And your Pn, that is the minority carrier concentration, will increase. And that is why the psi 0 minus V, that is psi 0 has decreased. That is why your psi 0 has decreased by an amount of V. That gets reflected even in the Boltzmann relation, because your Pn also will increase, as we have said that the external potential will definitely induce some sort of excess carrier in the N region. So this particular value Pp and Pn are the values at the depletion edge, that is here. This is the depletion edge. We are considering the values in the depletion edge, right? Now, if you also draw this Pp or the del P, that is the excess carrier concentration in the linear scale, it will be something like this. So these are exponential, because if you solve the diffusion continuity equation, it will be exponential in nature. So in linear scale, it will look like this. Okay. So that del P is equal to Pn0 into e to the power minus V by Bt minus 1. For electrons, it will be del N is equal to Np0 into e to the power V by Vt minus 1. So here your Np0 is less than Pn0, right? Which is understandable because the concentration or the doping level is higher in this case. So your Np0 is less than Pn0, right? Np0 is the minority carrier concentration in the P side, which should be less because the doping level in the P side is higher. So that's why you will find that this particular value, that is the del P value, is higher than that of that del N, right? And if you look at the flow diagram, you will find that the electrons that are coming from the from the right side, that is from the N side, they will directly go to the P side and will recombine with the excess carriers, right? Similarly, the holes that are coming from the P side will directly go to the N side and also will recombine with some of the excess carriers. So same will happen in the N side also. So some of the electrons will recombine with the holes that are coming from the P side, and the rest will cross the space charge as it is shown here and will recombine with the excess holes in the P side, right? That is how they are getting balanced. So these particular arrows are showing the recombination. And in depletion region, we assume there will be no generation or recombination. So that is also very important. We assume that in the depletion region, there is no generation and recombination. And that's why you will find when we discuss the current density, we find that in the depletion region, current density for both N and P is constant. That is, for both electron and holes are constant. Now let us get back to this particular equation and let us see the ratio Pp and Pn. So you can write Pp is equal to Pp0 plus del N and Pn is equal to Pn0 plus del P, because in both the sides you have excess carriers. Now, as we have said, at low injection level, your del N will be very, very small. So it will not affect the majority carrier. So this is PP0. However, in the denominator you will have PN0 plus del P. Now at the depletion edge, that is this edge, we can consider del P as delta P and del N as delta N. So that is why we have written delta P and delta N in these expressions in the depletion edge. So these are the values at the depletion edge. Now, if you take this and this equation, and if you subtract from each other, as it is shown over here, you will get the value of V, which is equal to Vt ln Pn0 plus delta P divided by Pn0. Just a simple algebra. And from here, you will figure out the expression for delta P. You can very easily get the expression for the delta P, and that particular expression will be Pn0 into e to the power V by Vt minus 1. So you can do it in your home. The expression will come as delta P is equal to Pn0 whole into e to the power V by Vt minus 1. Now you can see that the excess minority carrier has an exponential relation with the applied voltage. Delta P is nothing but the excess minority concentration in the N region. So the excess minority carrier concentration has a relation with the applied voltage, and that is exponential. And that is why you get the forward current characteristics as exponential, because forward current is nothing but due to the excess minority carrier concentration. Right? So definitely you will also have a relation, current voltage relation, which is exponential, because they are related to each other. So we will see as we progress. Now let us see the current term. So this is your device, where this is the quasi-neutral region and this one is the space charge region. Now if you plot the concentration in the linear scale, you will find that this is delta P and the relation is exponential. So in both the side you will find a plot like this, and from there also if you draw or find the slope, you will find this is nothing but the diffusion line LP, which is much smaller than that of the total length of the N region, right? And now if you find the current density also will follow the same nature, because they are related to each other. So if you find the slope function, you will find the current density in the depletion edge will be nothing but Q dP delta P by LP. Similarly, the current density in the depletion edge will be Q dN delta N by Ln. This is from the slope information only you will get, right? And the current in the space charge region will be constant, because we have taken an approximation that there is no generation and recombination in the space charge region. And if you now figure out the total current also will be constant throughout the device. That is J is equal to Jn plus Jp. So that also will be constant throughout the device. So definitely in the quasi-neutral region, this Jn will be something like this and your Jp will be something like this, right? Because your J is constant across the device and J has to be constant, right? So now if you put the values of Jn and Jp in this case from here, you will find that the expression will look like this. Now put the value of delta P and delta N, you will find an expression of this kind. So your J also has an exponential relation with voltage. So that's why you see in the forward bias there is an exponential relation between V and I. That's why the forward bias IV characteristics is exponential in nature. Okay. So in this lecture, we already have discussed built-in electric field and built-in potential. We have seen how this plot looks like for built-in electric field and built-in potential. We have seen the origin of these two things, why we get an built-in electric field, why we get an built-in potential. And then we discussed the considerations of p-n junction under equilibrium. So, how a p-n junction behaves under equilibrium, what are the different important concepts associated with that. We have seen the band diagram to some extent, and in the coming lecture we will discuss more about the other concepts of p-n junction. Let us conclude this lecture today. We will meet again in the next lecture and we will discuss those concepts, the further concepts in the subsequent lectures.